So, good morning again. Let's continue our discussion on Bluespec system Verilog. I would like you to make a note of few important websites, and also I would like you to install the Bluespec system Verilog compiler today and try to run it. As I said, Bluespec system Verilog, it was made open source 2-3 years back, and so there are multiple GitHub repositories. I myself am trying to figure out what is there in which repository. But there is one repository, blang.org. Please I'm putting it in the chat box. This is one repository you should be looking at. And there is this documentation. So here you can see tutorials, and here in the tutorials, the important thing for you is BSV by example book. So this is a book which you can use it as a reference when you get any doubts, but there are other books. There is one manual also. And well, in any case, if you go to Bluespec Classic refers to the Haskell version of Bluespec, but if you go to BSV_training, you will get a different, you will get, if you start from here, you will get slides and you will get some example programs, quite a good number of resources like how to do sorting in hardware and lots of other examples you can see. Yeah, so, well, I think this is, this one got, this is again the tutorial, the documentation of tutorials. I think you may not need this repository because I think if you just go here in the blang and from there navigate to documentation, you will find all the necessary resources, documentation. This documentation is very important because usually, unlike for other things, in Bluespec, you don't find much on forums. Most of the things that you have to look for if you get any doubt is from this documentation and any examples they have provided. Yeah, so I think under blang, they have 5 repositories. One is the documentation repository, which is important for you. The other is the compiler. And the other is libraries, BSC contrib. This repository has libraries, I guess. And yeah. And then Bluespec development workstation, I think it's a graphical user interface. It helps you in your many things such as module browser, schedule analysis, things like that. It can make your life easy down the lane if you learn to use Bluespec development workstation, because you will see, yesterday we have seen there are rules and the rules can interfere with each other. So they need to be scheduled. There is a scheduler which automatically schedules them in different clock cycles, things like that. But I think you will be able to clearly see those conflicts and how they are scheduled by using this, this development workstation. And then there is a test suite. I think you may not need to look into this test suite much. Okay. And what I would like you to do today is, this is this one. You should, I'm putting this here. You should install Bluespec on your machine by, if you click this link releases on this, then you will see the latest version, you may want to pick the right version for you, any of the star files, and install it on your machine. And along with this, you have to install iVerilog. I'm putting it in the iVerilog. You can just install on Linux using regular package managers. Other two things that are useful for you is BSc user guide and BSc library reference guide. These two things are very useful for you. And one more very important resource for you to understand is computer architecture, a constructive approach. This is an excellent book for computer systems organization, but usually we learn through architectural diagrams, know how an architecture for a single cycle processor or a pipeline processor looks like. Here you'll actually have the specification written in BSV. It's a very good book and you should read this book. So this book, I will send it to you after this session is over. And yeah, so now, as I told, so these are the important resources for you to keep in mind. So as I told, so the power of Bluespec is you will be able to express very complex designs easily. And in the last 5 to 6, probably more than 5 years, in the last decade, all the instruction set architectures such as IA32 instruction set architecture, IA64 instruction set architecture, MIPS 32 instruction set architecture, they are proprietary instruction set architectures. So there is an open source instruction set architecture called as RISC-V, which came recently. Recently means in the last decade. So I think Patterson and Hennessy and many other people came together and they came up with this RISC-V instruction set architecture. And once this open instruction set architecture is there, open instruction set architecture is there, there are many people who try to build processors for them, processors of various for various purposes, processors for the embedded systems domain or IoT domain, processors for maybe server class machines, things like that. So Bluespec company itself, they have come up with interesting processors using their Bluespec system, using their infrastructure. Like for example, Flute, it's a free and open source RISC-V CPU. That means you can go and see the processor code for this for the RISC-V CPU. RISC-V instruction set architecture looks very close to MIPS instruction set architecture. And then you can see there is Piccolo. This is a 3-stage in-order pipeline processor for RISC-V CPUs. Piccolo is intended for low-end applications, embedded systems, IoT microcontrollers, etc. And Flute, that's what we just looked at. Flute is intended for low-end to medium applications that require 64-bit operations, 10 MMU and more performance than Piccolo class processors. And Tuba, it's a superscalar processor. Okay, 3-stage pipeline processor, 5-stage pipeline processor, superscalar out-of-order pipeline. The same instruction set architecture, different processors are being released. And usually, these are all, this kind of development of processors just using Verilog is very difficult because the amount of code you have to write and many challenges. and HLS is just simply pain. Using C, C++, designing a processor is just a pain. It's not going to work to the best of my knowledge. What happened here? And then, so for within India, you know, in all our missiles and many defense equipment, we will be using microcontrollers, processors, but all these are manufactured from outside India. So if someone down the lane stops supplying these processors to us, let's say if you're shipping processors from US, and since now India is not taking a firm stance on this Russian war, if US says we no longer supply processors to India, then we will be stuck. Or we may get processors, but they may have some spyware in them, and they may start malfunctioning at the right when we actually want to use them. So we have to build our own processors. So IIT Chennai has a Shakti line of processors built. So again, this is possible because it's the power of the specification framework. Because otherwise, you know, processors can be developed only in companies such as ARM, Intel, with huge number of who has lots of manpower, money, because no, the testing, just not the development, testing, a whole lot of things needs to be taken care of. So all these things are possible because of this framework. Okay. So well, the reason why I am telling all this is there is a power. There is a very good, excellent power this framework has. Hey, there is. You should have blocked the view. No one is telling me that the view in the middle is blocked. Come on, guys. I'm recording this and okay. So yeah, so that is the story. So giving a motivation that sorry,
some part is still blocked.
Some part, it will be on the side, no, not in the middle, right?
This one's not interfering.
Yeah, okay. Okay, so the problems that you are working on, they are not that complex when compared with these kinds of systems, and you should be able to work on them in a reasonable period of time. And also to say, within our lab, we build a very, very complex overlay structure for processing the deep neural networks and for image processing algorithms. Pipelines. One PhD student, Jiaul, he is extremely good at this, and pretty much he built the whole thing, you know, single-handedly. The overlay architecture for deep learning neural networks and image processing pipelines. Okay, so now let's quickly review what we looked at in the last session. Okay, this is what we started with, and so to review, so we have this GCD a module in Bluespec system Verilog. It consists of 3 parts. One is the state. The other is how the system evolves with as time progresses. Time progresses in terms of clock pulses. And finally, there is an interface to every module. When we looked at the state, an important thing we discussed is, so this is a register. Here we are creating a register of length 32 bits, and this register holds data of type integer. Well, the hardware doesn't know that it holds data of type integer, but the compiler knows. So Bluespec is a strongly typed language. That is, at the compile time itself, we completely know the data type. All the data types we will be knowing. And because of that, all type safety checks will be done. All the type safety checks will be done at the compile by the compiler, and which saves, which helps us catch the bugs early on in the development life cycle. So imagine you generate a design, your synthesis takes 2 days, and then you try to put it in the hardware, and then you see some bug, or at the emulation time you see some bug. It's a emulation time, okay, I think it doesn't take much time, but when you after synthesis takes a lot of time. So you want to catch the bugs early on in the development cycle. And then there are two rules here. One is a subtract rule, and other is a swap rule. And there are predicates here, and if this predicate is true, a rule can fire in a clock cycle. And then there is a, similarly, the subtract rule, if the predicate is true, then it can fire. But then we have seen in last class, there are implicit rules and explicit rules. This predicate here, it's an explicit predicate. That is, it's very clearly given that that this rule can fire explicit predicate. So similarly, this is also an explicit predicate. So these two rules can fire only when the corresponding explicit predicates are true. And the second thing is there will be some implicit predicates, but in these two rules there are no implicit predicates. There are no implicit predicates in this. The interesting thing here is the two statements that you are seeing. In the case of swap, there is only one statement. So what happens is, in terms of the hardware, roughly what can happen is, if this is register Y, then the register Y, and this is register X, then the contents of these two registers Y and X will go to some subtractor, and then the output of subtractor, it will be fed back to the register Y. Via a multiplexer. We may need a multiplexer because if you see, the X goes to Y and Y goes to X. So what happens is there is one output from Y, which kind of goes Y. There is a multiplexer here. So Y goes to X, and then the output X goes to Y here. So if the swap rule is enabled, then X will be, this path will become active, and it will be returned to Y. And if the subtract rule is active, then the output of subtractor will be returned to Y. Okay, so yeah, so this, like this, a circuit gets generated, and so if there are multiple rules, and if there's a conflict between multiple rules, in this particular case, this swap and subtract are mutually exclusive rules. That is, if this predicate is true, subtract will be false, because X greater than Y and X less than or equal to Y, they are complementary rules. So if swap is enabled, subtract will be false. If subtract is enabled, swap will be false. Because of that, they don't conflict with each other. These two rules, they never conflict with each other. But down the lane, it is possible that a few rules may conflict with each other. That means they are ready to fire in the same clock cycle, in which case there is a rule schedule, hardware rule scheduler, which schedules them, and there is a priority also we can specify. That is, among all these rules, conflicting rules which are ready to fire, no, this rule takes a higher priority than another. Other important thing I would like you to appreciate here is these two are not sequential statements. X is equal to Y and Y is equal to X. So if you think about it, so you have this register X, the output here, and register Y. This is output here. So this goes and comes here. This goes and comes here. So what happens is if you are designing a positive edge triggered flip-flop, then at this raising clock edge, the contents of register X will be latched into, the contents of register X will be latched into Y, and the contents of Y will be latched into X simultaneously. So this happens in parallel. These two statements will execute in parallel. So remember that. And then there is a and then we have these external interfaces, start and result, and start will be enabled. You are passing A and B. Start is enabled only if this predicate Y is equal to 0, and result is this is an action method, means it changes the state of the module because it is updating the registers X and Y, whereas the result method, it's not an action method, it's just a result method because it is just reading the content, it's not affecting the state, but still it has a predicate, and only if the predicate is true, the result function will be enabled. And we have seen, there is this I underscore GCD, it's an interface. This module implements this interface, and this is the interface definition, and we can have a parametric interface. We can have parametric designs, so that the same parametric design can be used to instantiate different kinds of modules, just like the way we work in STL. Okay, so now again, just to review, so when you have a Bluespec system Verilog code, you can generate Verilog code, and it can go through take the FPGA path, or it can take the ASIC path. But before that, either we take the FPGA path or ASIC path, the first thing that we do is we simulate it using Bluespec compiler, Bluespec simulator, and it's a cycle accurate simulator. That means the number of cycles that we get during the simulation is very accurate, and that's what we can use. Okay, yeah, this is a test module. This is a test bench that we are writing. This is a very simple test bench. When this test bench gets invoked, state is this predicate is equal to 0. It tries to. There are two implicit. So there is a hidden. This is explicit predicate EP. And there is an implicit predicate here, that is, remember that you can call start if and only if Y is equal to 0. This is the implicit predicate. If the register Y is not equal to 0, then the go rule cannot fire. Right? So here finish, there is this is the explicit predicate. After the computation, so what happens is in clock cycle 1, the go rule will fire, and then in clock cycle 2, the finish rule is ready to fire because the explicit predicate is ready, but then the implicit predicate GCD.result, it's not ready because until this Y becomes equal to 0, we cannot call this, and this becomes equal to 0 only after the GCD computation is over. So yeah. So this is how this whole thing works. The cool thing, as you can see, that you can write your own test bench, you can have your module, everything can be simulated. So like for example, no, like let's say if you have a design which parses UDP packets, then you in the test bench you can keep sending the UDP packets, and we didn't see, we are not yet seeing we didn't yet see the hardware queues. Perhaps we will get a chance to look at it in today's session itself, in which case you can keep putting in the hardware queue these UDP packets, and the UDP parser can dequeue them from the queue, and it can parse those UDP packets. This is a slightly more complex test bench. Let's not go through this. So here you can try to understand this theory behind this whole maybe later, but I'll just give you a brief overview. If you have problem, it's okay understanding this, okay? We can take this up again some other time, but I want to give a overview of this. So what happens is, if you look at your whole system, this is your whole system. What is the right way to, so there is a state, so any system, it consists of a state, registers or VRAMs or whatever, and some combinational logic. Remember, combinational logic, it has only gates, it doesn't have any state. Okay, and then the output of this combinational logic, for the sake of simplicity, I will just use one line. This is a bus though. You can read the output of this combinational logic, and then let me do one more thing. Either and the input to the state, it can come from the external world, and it can come as a feedback also here. And sometimes, depending upon the design, it is possible that we may need a multiplexer here. There's an input coming out from here, and so something like this. And in every, your system keeps progressing like this. So what happens is the state of the system keeps getting updated in every clock cycle. So this is what it says. The state, the next state, it's a function of the current state. Okay, it's a function of the current state. And so here, if your system can be a collection of rules R1, R2, R3, R4, and associated with every rule there is a predicate pi1, pi2, pi3, pi4. And if these predicates are true, let's say the predicate associated with R1 is true, the predicate associated with R2 is false. If this is true, if this is false, then you don't go to the next stage. R3 might be true and R4 might be true. And remember, all these rules, they can potentially impact the state of your system. So the way, R1, the state transformation function, S is the current state. The state transformation function for rule R1, let's call it as delta 1. For R3, it is delta 3s, and R4, it is delta 4s. So all the rules that get fired, they can impact the state in a certain way, and how that certain way is how we write the code. So a delta S is a state transformation function that computes the next state values from the current state. Like for example, you have, if you go back here, So there are predicates pi1 and pi2, either pi1 is true or pi2 is false. So the rule body tells what will be the next state of the system. Next state, the system moves with every clock pulse. And this whole thing is kind of summarized in this way. This is the current state of the system, and this current state is and this current state, and also is fed to this predicate, this pi. And so here, so this is pi1. There are multiple associated with all the rules. You will have predicates, and all of them are evaluated, and there are enable signals that comes out that which tells us, depending upon which predicates become true. And then there are these next state functions, like delta 1, delta 2, delta k. Let's say if pi2 is false, then the state affected because of delta 2, whatever it is, it just gets ignored because the corresponding enable signal will not go up. Again, if you see here, this is a rule where I think f is a q, and what we are trying to do in this particular case is the predicate is we are checking if the queue is non-empty, I guess. If the queue is non-empty, then we do a dequeue, and along with the dequeue operation in parallel, we are incrementing this variable. So if this rule is, so what happens is if this predicate is false, then this doesn't happen. The enable signals doesn't go up and the dequeue doesn't happen. So anyway, roughly this is what happens, that there is a current state, we move from the current state to next state, and only those rules whose predicates are true will be enabled, and among the rules that among the rules that are ready for, let's say let's say the rules Ri1, Ri2, so on up to Rik, they are enabled, and if they don't conflict with each other, then all of them can be scheduled in the same clock cycle. But if Ri1 and Ri2, if they conflict with each other, then what happens is in one clock cycle, depending upon either the way the state gets affected is either Ri1 executes after Ri1 executes and then Ri2 executes, or the other way around. And it is possible for us to say, I prefer this this order rather than this, by specifying priority. This is what it is. Okay. Yeah, so this is among all the rules that are enabled. So there's a priority encoder circuit which schedules, which decides which rule should fire. So like, for example, if R1 and R2 are both are can fire, but R1 has higher priority, the priority encoder, it kind of enables Phi1 but disables Phi2. Phi2 is, let's say Phi2 corresponds to if R2 has to fire. I'm not getting into the details, but I'm just trying to give a high level picture. At some point, we can revisit this and understand down to the details. But we don't need to understand the details of the rule scheduler. All we have to understand is to summarize here. Yeah, so I will all I will say is there is our system evolves as say there are collection of these rules R1 to Rk. These rules tell how the state of our system evolves, and then so how the state of our system evolves, and these rules are not fired. Associated with every rule there are predicates. These predicates consist of explicit predicates and implicit predicates. If both of them are true, no, they will fire. Like for example, pi1 may fire, pi5 may fire, pi10 may fire, pi10 might be true. Similarly, pik might be true. So let's say these are the four predicates that turns out to be true. So that means R1, R5, R10, Rk, all these four rules are ready to execute. When all these four rules are ready to execute, if they don't conflict with each other, all of them can execute in the same clock cycle. They conflict with each other. Let's say R1 and R5 may conflict with each other if they are trying to dequeue the same queue, hardware queue, for example, maybe. Okay, so if there is a conflict between them, so we have to prioritize. That's the summary. And there's a scheduler, there's a hardware rule scheduler which automatically does all these things for us, and we don't need to worry about it. Okay, this is the summary picture. This is the summary picture. Any questions you would like to ask at this stage, please? You're all good? You can type in. How many of you are with me here so far? Can you put in the chat box? I just want to see how I am doing. Okay. Okay, great. So now let's take a deeper dive into into this combinational circuits. Give more examples to get more experience. So again, just to review, any system, it consists of some sequential components, some combinational logic. So here there is a register here. This structure, the kind of structure that you are seeing here, it is quite common when you are going for pipeline designs. Or like there is a module, let's say, so there is a register here. This could be a register or a VRAM block or something, and there's a combinational logic which reads data from here, does some computation and writes it into VRAM or some other state element. This state element can be a queue or something like that. Like for example, again, if you take the example of a networking stack, so this could be module M1, so which does some processing on the packet and then it writes it into some other queue, and there could be some other module sitting here which reads this state and does some computation here in the next clock cycle, perhaps. So adders, multiplexers, arithmetic and logic units with no state elements, they are all examples of combinational logic. Yeah. So now I would like you to take a look at what happens in the hardware level. You know, like in your digital logic course, you would have studied about a full adder circuit which will be used. If you are designing a 4-bit adder circuit, you have a sequence of 4 adders with 2 input bits, and this is a carry in bit, and this is a carry out bit, and this is A0, B0, A1, B1, like that, A2, B2, A3, B3. Okay, so now let's say if you want to design this circuit, you want to specify this. If you recall the logic from that course, from that, I think the sum bit is the sum bit that goes out in a full adder circuit. Now, when you take 2 bits and you take a carry in and carry out, the sum bit, this is C out, and this is the sum bit. The sum bit here is nothing but the exclusive OR of the 2 input bits and C in. So that's what is happening here. You are computing the exclusive OR of A and B. And remember, we are working on this A and B. They are not variables. They don't have any memory. A is a wire, B is a wire. Whatever the signal that is there in A and B, you do a exclusive OR, okay? And the wire that comes out, it is T, and you compute the exclusive, this is the T wire, and you take C in and you compute the exclusive OR of that here. This will result in this particular thing, and SC is the wire that is coming out. Similarly, the carry out is computed using this logic. We may just have to check this logic. I think if I am right, so this is nothing but AB plus C in times A exclusive OR with B is what C out. Plus means OR here, and we write this expression here. So the signal C out is like this. And this function returns 2 signals. One is S and other is C out, and that's what. So when you write a function such as this in Bluespec, then a circuit such as this will be generated automatically for us. But remember, Bluespec is a very strongly typed system. So you have to specify clearly what is A. We say A is a bit of length 1. And B is a bit of length 1 and C in is a bit of length 1, and the return value is 2 signals. So bit 2. This is how, this is a complete functional specification of the carry out bit. So Siddhant has a question. Siddhant, you can unmute yourselves and ask the question.
So in the first example that we saw, X and Y were getting interchanged and they were getting done in one clock cycle, getting it like it was done parallelly.
Yeah.
In this case, that cannot be done because T needs to be computed first before we compute S.
Yeah. So if you think about it,
so like will that be done sequentially?
No, it's not. That's not the right way to do it. Think about it. In this particular case, you can see wherever parallelism is there, it gets exposed. Like for example, C out, we compute A ANDed with B, and C in is ANDed with T, and A exclusive ORed with B. So in one clock cycle, let's say if it takes one clock cycle, has sufficient width to just do one gate computation. Then although this A exclusive ORed with B is at the beginning and A ANDed with B is written somewhere here, in the one clock cycle, this and this will be computed in the same clock cycle.
Okay.
Understood, no?
Yeah.
So, and in the next clock cycle, so although it may not, the clock cycle width might be long enough to do the whole computation in one clock cycle. Assuming, let's say, if that's the case, then what happens is these will be computed first, and after that these two will be computed.
Okay.
Yeah. So we'll not get into. Yeah. So, and I think in Bluespec, it defines some data types, byte, word, and like pair, and you can see there are parametric types already here, if you see, and yeah, so they are very useful, but when you are writing code, you can sometimes get frustrated also. Just warning you, but it's we need to get a hang of it. So here, yeah, this is an example of type error. You can see that that what we have just give me 1 minute. Yeah. So yeah, let's see. Yeah, so here there is a type error because this one generates a 1-bit value. So this whole thing generates 1-bit value. It's 1-bit value or signal, but on the left we are saying it should generate 2 bits. Then no, a type error automatically gets generated. So this is an example of a type check. So now comes, let's say now you want to design a 2-bit adder. So you take x and y, x is of 2 bits, y is of 2 bits, and you take a carry in bit C0, which is of 1 bit, and then so you use the 1-bit adder to generate this 2-bit adder. So you call FA as a function, and so what happens is, think of it in this way. FA will not be called. FA is in some sense will be inlined, because the circuit, it's not functions, they get inline. It's not like you call the function and you get some value. The circuit associated with FA gets inlined with corresponding parameters x0 and y0 being passed. You can see, this is the first, this let automatically infers the type based on what is there on the RHS. So CS0 will be of type 2 bits, bit hash 2, and similarly CS1. So here what is happening is this line will generate this. C0 is acts as a carry in, and X0 and Y0 go here. And this CS0 has 2 components. One is the sum bit, the other is the carry in. Now we are passing this carry in bit to the next full adder. Again, it's not a function call, circuit gets generated. So X1 goes here, Y1 goes here, some bits get generated, and carry out bit comes out. And finally, the return type is 3 bits because 2 sum bits and 1 carry out bit. So we are sending out 2 sum bits here, and there is a carry out bit here. So we are able to generate a 2-bit triple carry adder using a 1-bit triple carry adder circuit. And if you want to write a 32-bit triple carry adder, so yeah, before we go here, so either you can use let in, so that we can automatically infer the type based on what is there on the right hand side, or we use this. But this is the second one is better because it acts as a documentation of your hardware. Otherwise, you have to go to the FA circuit and see what is happening and all. So it's always better to use explicit types without using let, because your program, your system gets documented properly. Now, how do you write a W-bit triple carry adder circuit? So that is the cool thing here. I think let me move this one here. So you can see you are passing, this is a parametric type. No, W is a parameter. So two W bit values and one carry in, and you return a W1 bit value, and you write a loop here, and this loop gets unrolled. Okay, what happens is this loop, right now when you write this function, the compiler doesn't do anything, it just makes a note of it. Because W is a parameter, it cannot generate any kind of circuit. So at some point, if you want to use, yes, like for example, here on the last line, yes, even here, so this is, if you want to define a 32-bit adder circuit, you just have to use this syntax. Okay, the add n, this is the function that we have defined, and we just use x and y. You know, like x is a 32-bit value signal and y is a 32-bit signal. So what happens is the corresponding 32-bit version of this add n gets generated, and you have a new function add 32 which does 32-bit ripple carry addition. And if you want to do a 3-bit addition, we can instantiate it accordingly. So this is a very powerful, very powerful thing, because let's say if you are working on a convolution, you are taking an image and moving, you are taking a filter and moving that filter on the image. You can, there are convolutions, 3x3 convolutions, 5x5 convolutions, or then you don't need to have a separate module for a 3x3 convolution on a certain image dimension. Or like for example, even the image type can be parametric, because you can have a HD image or different images of different resolution will be there, where the length and breadth or the height and image width are parameters. So you can have write a generic convolution computation module where height and width are parameters, and the filter that you are applying, that dimension is also a parameter. And you write a parametric code, and depending upon what image you are working on and what image of what resolution you are working on and what filter you would like to apply on it, you can instantiate a specific module on it. Great. So you need to keep a few things in mind. When you write, you'll get some issues. Like for example, one thing you have to keep in mind, let's say. So here you should use, instead of I less than W, I think you have to use I less than value of W. And there will be some technical reasons, because it has some strong type system and W is a parameter. I'm not exactly sure. So there are certain nuances, and they are not actually nuances, they are very strong technical reasons, but many times we don't understand the whole technicalities behind these functional programming languages, their type systems, etc. So because of that, sometimes we just look at some example codes to figure out what is the error and how we can fix it. Okay, so yeah.
So in what case would just using W instead of value of W be correct? Or
that's what I'm not sure. This is the right representation. Like for example, they say W is a parametric type, so you cannot use W1, W plus 1, because W doesn't have any any semantics. So in fact, even here also they say don't use W plus 1. You have to use type addition T add hash W plus W comma 1 is the right way to go about doing that. If you just use W plus 1, I think the compiler will complain. Okay, similarly, you don't use W, you have to use value of W, because W is in the types world, and part of the reason could be W need not be an integer, it can be anything also, I guess. So not sure, I have to think about it, Siddhant, no answer for me.
Yeah, okay. Yeah. We'll look at that later.
Okay, so yeah. Well, this is what is called as static elaboration. That is when you define this one, and remember, loops doesn't have any, this is not going to be executed as a loop. When you instantiate a 32-bit adder circuit, then this whole loop gets unfolded, and and FA gets inlined. So there are two things that happens when we do static elaboration. One is inlining, that is FA gets inlined. Second thing is loop gets unrolled. So you get a big circuit associated with this for loop. Okay, so you really have to keep this in mind. The code that you write in Bluespec, it's not like it's a C code or C++ code. It's not going to get executed. It gets so two things happen. One is inlining. Another thing is from here to here unrolling. So these two things together constitute static elaboration. That is, static means that at compile time elaboration. So they are not because when this has to be done at the compile time, because we have to generate hardware. Okay, so
then you would need to look at the host code as well when compiling. Like if you are using C++ or like if you're using C++ to somehow interact with Bluespec, so then we would either need to specify what all kernels we need beforehand, and or look at the C++ code as well, because we wouldn't know like for what parameters the function needs to, like for what parameters we need to synthesize which kernels.
Can you repeat? Can you repeat again?
Right. So I'm saying if you're using C++ to somehow interact with Bluespec,
yeah,
that is possible. So then would we need to specify what all functions we would need beforehand, or would there be a way to?
We need now, like for example, if you are working with a you want to use a hardware queue with some dimension, anything that you want it to be in the hardware, it needs to be specified at the compile time, because this is not a program that is getting executed. This gets completely unfolded into a hardware circuit. So anything which requires no runtime thing, you will not be able to do it here.
Yeah. Yeah,
does it make sense?
So for that, do we look at our host code, like in HLS we have to specify what kernels we need beforehand, and then use them in the host code, like what kernels and how many of those kernels we specify, like only when we are synthesizing, we specify them in the makefile or something. So do we do that here as well, or like we are able to just see the host file as well and see what all functions are being called in the compile time?
I host file. Huh?
Yeah.
What happens is, the way I see it is, yeah, this is where a bit of challenge also comes. Let's say you have a hardware design, and so in the hardware design, let's say you have the host. So what happens is from host to this hardware design, you have to send packets through some to some queue which is present here. Okay.
Yeah.
And the hardware, when you design a module, remember in a module it will have this start or result or interface functions. So what will happen is there will be some module sitting here which reads data sent by the host and kind of pushes it into the queue, which the processing thing, what do I say, which which the module requires. I mean, there's a, let's do one thing, put it this way. So let's say if you want to call GCD, you have written GCD. This is your FPGA. On this FPGA, you have GCD, and then this is your host. From host, you cannot directly call GCD.
Right. Yeah.
So there are two possibilities. One way of doing it is you send that AB over PCI Express to the host, or the other way is you send it to the FPGA memory DRAM. This is your host DRAM. This is the host DRAM, and this is your FPGA DRAM. And you send it from here to here and from here to here you read. But in either case, you need to have some kind of a interface circuit module here, which reads data from the host and passes it to the GCD module and reads the results and sends it back to the host.
Okay.
Does it make sense or?
Yeah. So basically, let's say we have GCD for different types.
Yeah.
Let's say we have made a parameter as GCD, and then in the host you're calling GCD for let's say 1-bit numbers or 2-bit numbers, 3-bit numbers, etc.
Yeah.
So like they'll be instantiated in the GCD because they already have a queue for that.
Yeah. So we need to have those different modules. You have to you need to have a GCD for 32-bit GCD module, 64-bit GCD module. There will be separate hardware entities present here, because it cannot dynamically expand from 32 to 64 or 64 to 32, right? They will be instantiated. Okay. And the data to them will be supplied via some mechanism. You cannot just call GCD function as it is from the host. You have to transfer data. And there's a wrapper which kind of moves the data from the FPGA DRAM or the data that is coming from the PCI Express bus and supplies it to the GCD modules. Whether you want to send it to GCD 32 module or GCD 64 module, it depends on how you are interfacing with this circuit which is sitting on the boundary.
Yeah, well, understood.
All right, so I will stop here. Tomorrow again we will catch up. We will look at more involved things. But meanwhile, what I would like you to do today is install Bluespec, and specifically what you should do is, let me tell you one thing. Yeah. So when you install, you have to go and run this smoke test. If you go to this directory example smoke test, if you just say make, then it says whether Bluespec got successfully installed on your machine or not. So if you can do this, it will be great. Okay, if you can run this smoke test today, then that will be nice.